In this video, I'm going to go through an extended question on mechanics. It involves 8.1, 2, and 3 of the IB syllabus. I've also put a blank copy of the question linked down in below. If you liked this video, let me know and I can do more videos in this style. Okay, so this question starts off with a cyclist here at the top of the hill. It's going to go on the way down. Has this bump here that is part of a circle, and then down to where it's flat between C and D. It says, first of all, calculate the gravitational potential energy lost by the cyclist traveling from A to B. So there's a few different ways that we can do this. We can first calculate the gravitational potential energy at A, and then do the gravitational potential energy at B, and then find the difference. So let me start with that. We've got the equation potential energy is going to equal mgh. The mass they give us 72. Remember, when we're working with energy, if you don't have a mass, just leave an m, because odds are it's going to cancel out somewhere later. 9.8 for g, because that's what's written in our data booklet, and the height here is 36. If I pick up my handy dandy calculator, I'm going to put all the sig figs right now, and then we can do some rounding later. I'm going to do the same thing for at B. Now the difference is just going to be the subtract between the two of them. Now I've got way too many significant figures here, so let's go back and see how many I should use. Well, 2 significant figures, 2 significant figures, 2 significant figures, and they're being multiplied. So my answer should only have 2. I'm also going to write it as kilojoules because 1, 2, 3 right here. So this is about 16 kilojoules. Now I said there was another way we could do this. We could have actually just calculated the difference in gravitational potential energy. And in this case, the mass is constant, g is constant, so it's actually just the difference in height. And if I had have done this, 72 times 9.8 times the difference is 36 minus 14, 22, and I would have been able to get to my answer here as well. Either way is fine. Now let's check to see where we'd get the marks. It is a 2-mark question, so 1 would be being able to calculate gravitational potential energy. And to be honest, even if you just calculated one of these, I think you'd get the first mark. And then the second one would be to get the final answer. So if I did it this way, there would be the first mark, there would be the second. Part 2 says, from A to B, 30% of the gravitational potential energy is lost and converted to kinetic energy. Show that the speed is approximately 10. Now remember, when they do the show that, this is rounded to 1 sig fig, so I don't expect to get the answer perfectly 10. So from our previous question, we had that the change in gravitational potential energy was 16 kilojoules. I'm actually going to be using the unrounded answer in my calculations, just to make things a little bit easier. That number should already be in my calculator. So that means I have 30% or 0.3 times that mg, and we have our change in h, and that's going to be converted into kinetic energy, 1/2 mv squared. Notice my m's will cancel out. Now if I'm going to rearrange for v, I'm going to have to take this 1/2 to the other side, so that becomes 2 times 0.3 times g times delta h, and I'm going to get rid of that square. Picking up my handy dandy calculator, I get 11.4 meters per second. Now remember, I kept the extra decimal places, and now that is approximately 10 meters per second when rounded to 1 sig fig. So let's check. This is a 3-mark question. Where will I get my marks? Well, I'll get 1 for this line right here. I will get 1 for the rearrangement and changing around, and then the final answer. Now remember, I said final answer there, but it's actually not this. This is given in the question, so I have to show my substitutions in and the unrounded answer. This line would have been better if I had 9.8 and the 22 right here. Okay, so now for part 3, it says state what's happened to the remaining 70% of the energy lost between those two. Well, that's going to go into thermal energy. And that was created when we had work to overcome friction. And that's just going to be our 1 mark. Now, I have a couple things I want to point out here, though. So first of all, notice I said the phrase thermal energy, not heat. The definition of heat is the transfer of thermal energy from one substance to another due to temperature change. That's not what's happening here. It was created by friction. So therefore, if you actually said it was transferred into heat, technically that's not correct. And usually the IB is very big on using the proper term of heat. Leave that for theme B. Okay, so we're down this hill, we're up here now at B. And it says we want to draw the forces when we're at B. So we always are going to have force due to gravity pointing downwards. And at B, we're also going to have a normal force upwards. Now, I don't know the size of the normal force, but I do know the normal force cannot be greater than the force due to gravity. If the normal force was greater than the force due to gravity, I wouldn't actually be able to stay on this and actually do this circular shape. We'll talk more about that in the next question. But for now, as long as Fn is shorter or equal to Fg, then we're going to give 1 mark for each one. Now, please note, it does say label. You can label this as normal force. You could have written the word normal. You could have written the word reaction force. In the previous syllabus, we would have used the capital R. All of that would be acceptable, except right here, you cannot just use the word gravity. You also could have used a W for weight. Now, this question should say 3 marks here. Using a speed of 10 meters per second at a radius of 25, determine whether the cyclists lose contact with the road at B. First of all, we're going to state what will be the defining factor about whether or not it loses contact. Well, this is centripetal motion. We said that there's a force due to gravity pulling down and a normal force pushing up. So that actually gives us the centripetal force would be always towards the center of the circle. That's going to be Fg minus the normal force because it's pulling away from the center of the circle. Whether or not it makes this complete circle and stays on the road will be as long as we have a normal force. So what we're going to say then is the cyclist will lose contact with the road when the normal force equals 0. So let's go back to my equation here. I'm going to put that as 0. So centripetal force, our net force towards the center, mv squared over r. The force due to gravity, mg. My masses cancel out. If I rearrange this, I'm going to have my velocity, r goes to the top, rg, get rid of the square. Substituting in my numbers, the radius was 25 meters, 9.8, and this gives me 15.65 meters per second. Now let's double check. I have more sig figs here than I need. 2, 1, well, we'll never go down to 1 significant figure unless I'm talking about uncertainties. So I'm going to say this is approximately 16 meters per second. Now, let's double check that I've answered the question. Determine whether the cyclist loses contact with the road. Well, I have the speed at which they would go when this goes to 0, but we are going slower than that. Since the cyclist is going slower than this speed, they do not leave the road. So 3 marks. We'll get 1 mark for clearly defining what happens when you leave the road surface. I'm going to get another mark here. And then again for saying that no, they do not leave the road. Part C, by the time she gets down to here, she's now only going 9.4 meters per second. She does not pedal on the flat section from here to here and comes to rest after 38 meters. Determine the deceleration of the cyclist. Well, we've got a flat place and I'm just slowing down so I can use SUVAT. The distance they travel, 38 meters. My final speed is 0 because I stop. Initial one being 9.4 meters per second. And I'm looking for the acceleration. Remember, the word deceleration is just an English word. The scientific word is acceleration. Could be speeding up, slowing down in a positive or negative direction. Go to my data booklet and I find the equation that has all of this in there. V squared equals U squared plus 2AS. And in this case, we know this value is 0, making my algebra so much easier to solve. A is going to be, move this to the other side, negative of U squared. Now, notice that negative is before this, so it actually does not disappear with the square. And 2S. So the negative 9.4 squared over 2 times 38. And this is going to give me, with my handy dandy calculator, 116 meters per second squared. Again, let's double check these sig figs. 2 and 2. This should be rounded to 1.2 meters per second squared. I would get 1 mark right here for all this work and substitution, and then 1 mark for the final answer. Assuming air resistance is negligible, calculate the coefficient of dynamic friction. Well, if we don't have any air resistance, that means that the net force acting on the cyclist is just the force due to friction. So mass times acceleration, and the force of friction is going to be the coefficient of dynamic friction times the normal force. And in this case, we're traveling flat against the road, so that means the normal force is just going to be equal to m times g, and my mass is going to cancel out. So mu d is going to be the acceleration of my cyclist that I just found in part 1 over 9.8. So it's 1.2 divided by 9.8. And that's going to give me 0.12. No units because the coefficient of friction is just a ratio. So that's done. And I used more decimal places and I've just rounded here. So where will I get my 2 marks? I'm going to get 1 for setting it up and 1 for the final answer. We've got a safety netting placed along the side of the course. We have a person that is 84 kilograms hitting it at this speed. So they're slowing down even still. Calculate the magnitude of the impulse exerted on the cyclist by the barrier and an appropriate unit. So first of all, impulse, sometimes used as letter J, that is just the change in momentum. Mass times velocity. And in this case, my mass is constant. It's only the velocity that's going to change. So change in velocity would be final minus initial. Well, I stop. Minus my initial is 7.2. And picking up my handy dandy calculator, 604.8, which, and this would be a negative sign, would be negative 600 units. Well, this is just mass times velocity. Impulse or momentum does not have a special unit, so this is just going to be kilograms from the mass and meters per second from the velocity. So it is 2 marks and it tells us to state an appropriate unit, so that's going to be one of them, and the other will be for the 600. Now, one thing to note is since magnitude was asked for, that negative sign will be ignored. So this would be a chance if you forgot to write down by accident, or you had these ones in the opposite direction, it really wouldn't matter. So now we've got two things. We had the safety netting, which would stop it in 0.45 seconds, or if there had been a rigid metal fence there, would have stopped them in 0.012, much faster. Calculate the average force in each case and explain why the netting is safer. Well, we're going to use Newton's second law in its general form. F net is the change in momentum over time. And in the previous question, we have already calculated the change in momentum. 604.8. Remember, I'm going to use the unrounded answer in my calculation, and then I'll do rounding later. And we're going to do it for both cases. So first of all, for the netting, it's going to give me approximately 1,300 newtons. Now, for the metal fence, that's going to be approximately 50,000 newtons. Now you might say, oh, question's done. No, let's double check. I calculated the force in each case. I now need to explain why the netting is safer. So the netting is safer because the impulse takes longer, causing a safer, lower force on the cyclist. Lots of people want to miss out this last part, saying, this is why it's safer. I also want to point out one more thing. In everyday English, we sometimes say that forces are absorbed. That is in everyday English, not a science phrase. The force isn't absorbed. It doesn't disappear somewhere. It's because we have a lower net force or a lower average force acting on it. That's what's made it safer. Now, afterwards, they must have sped up a little because now the speed is 12.4. On the flat ground, the total resistance force is 18 newtons. So I need to go find the equation that has power in it. This is an equation that gets used incorrectly often on these exams. Power is going to be a standard net force times a constant speed. If I want to know the power output, I have to have a single value here and a single value here. This does not work when we have acceleration because the velocity would change. So this is just going to be 18 as my force times my average speed, 12.4. Pick up my calculator. Double check 3 significant figures here, but only 2 here. So that means I need to go with the 2. So this is approximately 220 watts. So I hope that's helped you, giving you the blank question to try on your own, and now going through it together. Let me know if it helped you out and you want to see more of this kind.